Good afternoon. I'm Scott Lowe. I'm here at Gridstore headquarters where I'm joined by Kelly Murphy, CTO and founder of Gridstore, and Shri Agarwal, software architect for Gridstore. Thank you, gentlemen, for hosting me today for our discussion.
Thank you. Great that you could join us.
Thank you for joining us.
We are going to talk about the Gridstore architecture, which is why we have a whiteboard here in front of us. So how are you guys built? How did you decide what did you decide to build, and how did you decide to build it?
The simplest way to say what we built is storage that's purpose-built for virtualization. So if you think about where storage came from, over the past 20 years, it's kind of been this architecture where you had a server sitting on top of storage. When you put virtualization in the center of this, all of a sudden everything changed. The problem is that the storage doesn't know anything has actually changed above it. So what you have is this number of VMs all writing I/O, coming through a hypervisor, and in order for these VMs to be able to move around, they actually all have to be talking to the same storage and the same LUN on that storage. So you get this problem of the I/O blender, where all the I/O is actually blending together. You get a lot of random I/O and a lot of poor performance. It also leads to a lot of complexity when you think about trying to do things like snapshot and so on. If you have 10 or 20 or even 100 VMs all on the same LUN and you want to snapshot just a handful of those, you now have to snapshot all of them and replicate them and so on. So it becomes much more complex, and it's really difficult for storage, traditional storage, to work in the context of virtualization. So what we did that addresses this is an architecture we refer to as software-defined storage. We use this concept, and instead of having a physical controller sitting down here, we virtualize that, we move it across the network, and we actually put it right under the hypervisor. Okay? And what that does is it effectively creates individual storage stacks for each of these VMs.
Because a controller that has awareness about what's happening above it,
exactly,
which it didn't have before.
Exactly. So now we can stop that blending from happening. Okay. And once you have that lane created, now you can actually do some interesting things with the I/O. So you can actually optimize the I/O. You can look at it, is it small 4K writes, is it large sequential reads or something like that. They're not blending together anymore, but we can optimize that.
And it looks like you would also end up with lots more visibility. I mean, I think that's where you're going here.
Yes.
And which would open up a lot of possibilities for being able to potentially manage that storage, which we've been able to do before.
Yes. So manage it on two levels. One is I can now prioritize I/O for this VM versus this one. Okay, I can give more resource to this guy. So things now like quality of service. And quality of service in the context of storage with Gridstore is very different because we're actually at both ends of the wire. So our storage is sitting down here. These are individual storage blocks or 1U units. They scale out. We have software that sits on all of these, so all the endpoints. And then we're also sitting up here, and we can control the flow very efficiently across the network. So you think about like a network quality of service, we're effectively bringing the same thing. If you look at a traditional model for quality of service where it's just in the array and all that I/O has been blended together, maybe this guy becomes that noisy neighbor, the I/O is all piling up here, it's too late to do anything about it, right? So we can now put limits on this guy up here. We work in conjunction with Hyper-V's limits and reservations. So we can actually put a limit on this, we can put a reservation on this to make sure he gets 5,000 IOPS and make sure he only gets 100 IOPS. And the storage is also working then very efficiently here. The other aspect of it is you've got multiples of these. So you can see multiple different hypervisors, and because we have an end-to-end view, we can actually control that across sets of hypervisors as well as physical servers.
So what you're saying is basically when you scale multiple systems, the virtual controller itself doesn't scale, but it has the virtual controllers in each system can talk together and act as one?
Well, they're actually, think of it as this, if this was the unit here, a hypervisor, okay, and you got multiples of those,
yes,
that virtual controller is going to replicate with them. It's just software. It loads, it's a driver. It looks like a disk to the server. Okay, you can have multiple disks on that server. But really what it's doing is inside creating these lanes.
Now, if the virtual controller started to see that there was potential contention going on at a host, because it has a visibility up the stack too, could it take proactive action and say, okay, this VM is mission critical. Maybe we move you over to another host because I'm seeing potential storage related issues on this host.
This will fit in the clustered environment, so that VM, that'll be a for the administrator to actually make that decision,
Right.
or we could signal that say, look, this is being strained, it's not hitting its requirements or its minimum reserves that you asked for. Here's your options, and they could move that. And yes, then it will just talk to the virtual controller. It'll access the exact same storage and so on.
So one thing what I want to add with that is so we detect something called hotspot, which is basically the resource which is getting contended. So we try to move it offline. So whenever we detect hotspot on our storage side, we move the data when he's not using it. So we try, so we fix the problem proactively as opposed to hitting it kind of.
Yeah, so that's actually happening down here in the storage itself. So if there's certain people hitting, say, a set of nodes and it's just really heavy activity, but we have other ones sitting over here, we can actually start to move data around it.
So how are your customers how are your customers benefiting potentially from this architecture? If I'm a CIO sitting at my desk and I'm talking to somebody, what does this mean for me?
Probably the most important thing is it can, if you look at the critical issues for virtualization, the number one thing people complain about is performance. When they virtualize VMs, they run slower. Okay, a lot of that is to do with storage. So the first thing that we're able to do is increase performance. So this idea of being able to dynamically accelerate each of these VMs is a key aspect of that. Also that quality of service to make sure that, a typical environment is 80-20 rule. 20% of my workloads are really important. Make sure they run well. Okay, so really it's about performance and that kind of granular manageability. So I can really allocate the resources I want to. Instead of having this blending kind of all for one type of a scenario, I now have really fine-grained control.
And another model with this is like a scalability basically. So you don't buy, a lot of storage to begin with. You buy as brick kind of model.
Right.
Yeah,
so
that's kind of where this aspect then comes in, is that, again, having the virtual controller sitting up here allows us to talk directly to underlying storage nodes. We don't have a cluster in there, we don't have a backplane or anything. They talk directly and in parallel, which means we can keep scaling that.
So you don't have to worry about like a global distributed file system and all that stuff, because you've got because you're also leveraging Windows a little bit here to help let it do what it does, right? Through the driver model. And then scaling that way. So there's actually more simplicity in this design than we may see from...
It just looks like a local disk that can just keep scaling.
Very nice.
we are a store port device over there in the local host.
Yes.
Okay.
So it's like a store port regular SaaS device, though it's virtual.
And to kind of summarize just what those three different things, that we just did some benchmark analysis with third party, and it basically came back that we could run at these VMs at 4 times the performance at literally half the cost.
That's impressive.
Yeah, and then you can scale that, so you can just keep scaling it as you want to. Here with these storage nodes, they start at either 4 or 12 terabytes, so it's a minimum of 12 or 36 because we use 3 as a min.
Okay.
And then you can scale that up to 250, which would be 3 petabytes.
You also have what's called the performance and a capacity node, right?
Yeah.
So how are you leveraging solid state in the architecture? Is that as a caching mechanism, or is that a storage tier, or both?
It's cache. So it sits on the storage nodes. It's a write-back cache, a persistent write-back cache. And if you think about that, what we're doing is putting a bit of flash into each of these, or a set of these, and then our I/O is actually being distributed across that. So when we write a block of I/O, it goes across, say, 4, 6, or 8 of these nodes. So you actually have quite a large aggregate of flash, even though we're using, say 500 gigabytes in each of them. But now when you actually do an I/O, you're looking at a pool of, a couple terabytes. So you can use low-cost, affordable flash in smaller sets. You don't have to have really large sets, which makes this affordable. But because of the architecture and how it scales, you get the benefit of having really large caches.
Very good.
And second thing, it helps us with deblending impact. So because we are writing to flash and it's a write back, so we don't have that seek penalty with the disk. That's one of the biggest advantage what we get.
Yeah.
Thank you, gentlemen, for this look into the Gridstore architecture.
Okay, great. Thank you.
Great, thank you.
And thank you for watching.